Okay, so reviewing time. Sphere of radius A centered at the origin can be described like this. This should be familiar, at least this much, from what you've done with regions of 2 dimensions. Now it extends easily to this. Of course, we did this in the last class, so this is kind of a review, but then we're going to extend it to do an ellipse. Okay, so here's how you describe circle radius A in the XY plane. Here's the limits on Z given a point XY in the plane. Picture. Here's your circle down in the XY plane, radius A. Here's a point XYZ, XY0 in the XY plane. And let's come on down and look at this. Zoom in on a little bit. Okay. Again, point XY0 here. XYZ is on the sphere. So using the Pythagorean theorem, you got this little blue triangle that I don't say too much about. But dimension of this triangle, you got X and you got Y, so that the hypotenuse is the square of X squared plus Y squared. And the hypotenuse of this little blue triangle is one of the legs of the right triangle we get here. So we have square of X squared plus Y squared is this leg. Z is going to be the other leg. And since this point XYZ is on the sphere, the hypotenuse is the distance from the origin to the point, which is the radius of the circle A. From that, you can conclude that Z is the square root of A squared minus X squared minus Y squared. Okay, and that should be minus. Okay, and then of course below the sphere we get the same triangle, similar triangle, and we conclude that Z goes from the negative to the positive square root of A squared minus X squared minus Y squared. So the current question is, can we describe the ellipsoid? Now I move the camera here. I'll get used to this eventually. Describe the ellipsoid. X squared over A squared plus Y squared over B squared plus Z squared over C squared equals 1. Inequalities, in other words, analogous to this. So first of all, like we did here, let's just start out in the XY plane. I'll comment, we could start out in the YZ plane or the XZ plane. If you have any ellipse in either of those planes, you could do this equally well in any plane, any of the coordinate planes. But we're going to choose the XY plane, kind of our default. In the XY plane, Z is 0, so we have X squared over A squared plus Y squared over B squared equals 1. Now, as we showed very early in the course when we were starting to look at quadratic surfaces, how do you graph a conic section centered at the origin? Okay. And in this case, you're going to construct, in the case of an ellipse or hyperbola, you're going to construct this little square or rectangle, going from negative A to A and negative B to B. And that's going to work for X squared over A squared plus Y squared over B squared equals 1. And it would work also for X squared over A squared minus Y squared over B squared equals 1, which is hyperbola. Okay. Or Y squared over B squared minus X squared over A squared equals 1, which is also hyperbola. Hyperbola would have asymptotes at the diagonal line in here. Okay. Now we went over all this, so you might want to review some of the very early videos, or just review how you graph conic sections. And of course, conic sections are supposed to have been covered in the regular course. Okay. And if they weren't, you just got to dig and figure them out. Okay. This is pretty much this is a good bit of it. Anyhow, so having drawn this rectangle, your hyperbola would have graphs that come out to the asymptotes and then come in here at a vertex and then come out or do it up here, and it's easy to see which, if you just think about the numbers and so forth. But now to the point, your ellipse fits inside of here. So now your question becomes just like here, you know, your first question was, okay, here's a value of X, we fix X, and now what are the limits on Y? Y goes from what to what, okay? X can be any number between negative A and A. For any X, there are limits on Y. And then for any XY, there are limits on Z. We start in a plane. So here's our picture. We have an X. What are our limits on X? You know, what's the value of X here? What's the value of X here? Okay. So if we figure that out. And also on the video, I didn't come down quite to the picture. Okay. Here's the picture in the XY. Should be familiar. Given a value of X, what is the value of Y here? What's the value of Y here? So Y is going to go from this value to this value. Okay, people having a little trouble with this. A couple of attempts seem to be kind of okay, but you know, here you are in the XY plane. Now you want to describe this region by inequalities. Well, you can let X go from negative A to A, and for every X, you determine what's the coordinate of this point, what's the coordinate of this point, and then if Y goes from here to here, then you've got all the points in this line. Okay. And then you go to a different X and you do the same thing. And you got all the points in that line. And if you go from negative A to, if you let X go from negative A to A, then these lines are going to just sweep out this whole ellipse, right? Okay. You're going to get a series of lines, infinite number of lines that give you every point on the within the ellipse. Okay, every point within the region bounded by the ellipse. A minute ago I said every point on the ellipse, and that wasn't quite right. Okay, so we have the equation here. If you got X, how do you figure out Y? If you know the X coordinate of this point, how do you get the Y coordinate? You solve this equation for Y. Okay. I mean, if I tell you X equals 4, and hopefully, you know, A squared is bigger than 16, okay? If I tell you X equals 4, you're going to have just numbers here, 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 and be able to solve for Y, right? Okay, so what do you get when you solve for Y? Well, and I think you might have had it, you're almost at, okay? There's one thing there that didn't quite look right. You're going to subtract X squared over A squared from both sides, then go 1 minus X squared over A squared. Then you're going to multiply by B squared, right? You're going to get this, right? And then you're going to take the square root. Or depending on what form you want to put this in. That could be B squared or B squared minus, you know, just distribute through with the B squared, right? Or probably preferable. I think we're into the watermark here, and I think I'm writing below. Actually, yes, I did have this. Okay, well, solving for y, you're gonna get this. Could be expressed like this. Really, I think I would prefer myself to use the form b squared times quadrant of 1 minus x squared over a square root of a squared. And 1 minus x squared minus x squared over a. And this is equivalent to this. Let's make sure you put this over common denominator, you're going to get an a squared b squared, right? Minus a b squared x squared. So you have your a squared b squared, you have your minus b squared x squared. And the square root of a squared is going to be presumably raise a positive number. Okay. Okay, well, what do we know now? At this point, we know that f goes from negative a to a. And y goes from negative square root of could be any of these expressions. No, I'll use this one because I can't start the form of that one, but that's less than or equal to y. Less than or equal to the square root of f. That's kind of small because it in the self room. Okay. Now it goes from negative this to positive this. Because this is the coordinate of this point, the y coordinate of this point, where x is the x coordinate. And this is a y coordinate of this point. And y could be any number between here and here. If you let y take every value between here and here, you get this whole line. Nothing outside. Everything you get inside on the boundary of the list. Then again, if you let x go from negative a to a, you're going to get all these lines inside and on the boundary of the list, right? Okay. Well, now we got to take account of z. What are you going to do about z? Let's see if you can get that. Okay, so now the question is, given a point x, y down here, point x, y within the ellipse, point x, y that satisfies these two inequalities. Now what are the limits on z? I can prove a bigger statement. If x, y satisfies our inequalities, and there's this point above and below on the ellipse. and all points between okay, I didn't say that right. On the ellipsoid, okay? And I should say on the boundary. Boundary of the ellipsoid, okay? So let's make sure that's going to show up. I'll eventually get less clumsy with this. Okay. But in all points between the 2 points in the boundary of the ellipsoid are within the ellipsoid. So what are the coordinates? What are the z coordinates? Well, let me point out, you've already solved the inequality, talking about why you solve the inequality. And this is a statement that works not just for ellipsoids, but paraboloids, for any surface, okay? If you've got the equation of the surface, then you need to figure out where it projects into one of the coordinate planes. And sometimes the coordinate plane you want to project into isn't the XY plane. For an ellipsoid, it could be any of the 3 coordinate planes. Okay. Surface might be complicated as heck in its projection down into the XY plane, but have a simple projection into the XZ plane. Okay. So you would want to start with your X and Z coordinates, inequalities describing your X and Z coordinates, and then figure out how the Y coordinates work. Okay. So anyhow, in general, you do this sort of thing. You figure out the inequalities in some plane, project into, and then for an arbitrary point X, Y, say in that plane, you figure out what the limits of Z are. What's the Z above? What's the Z? What's the highest Z? What's the lowest Z? And presumably everything in between will be within the surface. Okay. As long as there aren't any holes in the surface. Well, I'm not going to worry about that right now. Okay, so what are the Z coordinates of these 2 points? Well, just solve. Equation of the ellipsoid in this point. But if it's a hyperboloid, then we would substitute hyperboloid for ellipsoid, right? Or if it's some surface you don't know what to call it, just call it the surface, okay? And I'll go again. Okay. So we got X squared over A squared plus Y squared over B squared. Z squared over C squared equals 1. So Z is plus or minus square root of okay, square it off. Okay. I think you have the c squared inside the parentheses. That factors out. I'll get a c there. Okay, so now we have a complete description of our website, and we can set up an interval of that website. So our website is and let me check my solution down here. So it doesn't feel right. No, it's good stuff. Okay, so the website is that's right. I'm going to write this in just a slightly different form. Let's say we have negative b over h times the square of a squared minus x squared. Which is just what I had before, but I factored out the b squared. It was in the didn't follow it. And then z put the c out in front. Okay. So now, what's the volume? That's the volume of the website. Okay, well, we start with the ellipse and the XY plane. And we pick, well, what do? What does an integral mean? We partition, in this case, we partition the x-axis. Okay. And we take, and I'm not going to write off partition and everything, go back and review, so we can see what we're doing here. But we take the typical interval of the partition and a sample point. Okay. We let our y go from here to here, whatever is dictated by whatever sample point we happen to use. So now we got a rectangular region. Okay. Y goes from here to here. Here to here, right? So you got this rectangle. Okay, so we start out by partition the X interval, typical interval of partition. Y goes from here to here. So we partition the Y interval by we get little rectangles. And for every point within this ellipse, it's in one of these rectangles because it's in one of the X partitions, one of the intervals of the X partition. It's in then one of the intervals of the Y partition of that particular strip. Okay, the rectangle corresponding to that particular strip, just as we talked about previously. Okay. Then what? Okay, let's see. We got some more space over here. So over there. One over. This is them. But there we have it. Okay. So here's a typical interval. One of these rectangles. Okay. And now we've got a interval that goes above and below the axis until it hits the surface. Okay. So now we got the on above and below. Or to the rectangle. Okay. Look at it. What do? We partition this. And we get little cubes. Like I said, bottom is a prism. It's a rectangular prism. Because we have a sample point within this X by Y, the delta X by delta Y interval. And you take the altitude up here and down here based on that sample. Okay. Partition this prism. I'll say rectangular solids because I don't want to write out rectangular parallel pipe. Okay. Takes too long to write parallel pipe, although rectangle. Okay, that makes sense? That's what we're doing. And then we put all these together and we get a very good approximation to our ellipsoid. So our partition for x goes from negative a to a. We're given x value in the partition. We partition the interval. There it is. Okay. Negative b over a squared of a squared minus x squared b over a squared of x squared. Okay. And then we're given x, y in one of these little rectangles. We partition this. Partition z from here to here. If I read it to the point. Okay. And that gives us so approximate volume is this. This approaches triple limit. Myself trying to limits. Okay. Well, these, which is a limiting expression for finite delta z's, okay? Call it an infinite decimal line. And what are the limits here? Well, see, and here's your partition. Okay, your partition is, K is 0 down here, is P up here. Okay, K would go from 0 to P. Meaning that your Z values would go from negative C square root of 1 minus x squared over a squared minus y squared over c squared to square root of 1 plus x squared over a squared minus x squared minus y squared over c squared. Okay. Now, how did you get these XY rectangles here? Well, you partition the Y values in the strip, in this rectangular strip here. And those Y values go from this to this. Okay, now, I really didn't try to leave myself enough room. I think it's ever happened. But I did. Okay, so now we got to go from here to here. And that's with respect to 1. And then, of course, x goes all the way to this. This is why these are the limits in your energy. Okay, now we got to digress and talk just very briefly about trigonometric substitution.